Right, so we will get the solution of the entire problem. Okay, since the what equation in check point 10.1 and the explicit boundary condition at r equals to r in check point 10.2 it's linear and homogeneous. Okay. The superposition so use till the RT equal to okay, so this is superposition. Is also a solution of the boundary value problem. Okay. Now we set, so we setting t equal to 0. So we have U filter R0, which is equal to summation m from 1 to infinity am j0 alpha m capital R, which is equal to fr for r from 0 to okay, from the initial condition in 10.3. Okay. So this is from, by looking at this form, we find that, what is that? This is actually the Fourier Basel series representation of f of r, right? So this is actually the Fourier Basel series expansion, representation or expansion, that's fine, of the function for R. Okay? And we know that this expansion is complete. And we know very well about the behavior of this series. Okay. Where am, so we can find the coefficient. The m is by our formula. So it requires information about the Basel function of the first kind of order 1, J1, okay? We need J1 to compute this value. Okay, or m. Right, so now we know how to find the AM. Okay, the coefficient. So m can be determined by the initial displacement. Okay. Also, the partial derivative of U tilde with respect to time, so this is the velocity, minus lambda m, am, sine lambda mp, plus lambda m, em, cosine lambda mp, times j0, alpha m, alpha m r. Okay? Implies that U tilde p, near p are 0. The initial velocity becomes to lambda m, em, j0, alpha m, equal to GR for OR. Okay? And again, so from here we know this is the Fourier Basel series representation of the initial velocity GR. Where we know how to find lambda m times bm, which is equal to, again, r square j1 square alpha m from 0 to r j0 alpha m. Okay, so solve our problem. Of course, a remark. This is a formal solution. The entire problem. We have to check that it is indeed okay, the actual, the true solution. By justifying that the partial derivative is equal to and so you have to check that. We can exchange the partial differentiation with the infinite sign. Okay? We have to check that. Okay? Possibly by using 11.3 starting point D, and the wire truss. Yes. For any problem, okay, you have to check that. Because you are considering an image series, okay, so you have to check. The partial differentiation is exchangeable with the image sum, the series sum. Okay, but for this we have gained some experience. Huh? Okay, so the next topic is about Laplace equation in cylindrical, and spherical coordinate. Okay, we know the Laplace equation in 3 dimensions. Okay, so this is in 3 dimensions. Okay, so cylindrical coordinate. In cylindrical coordinate, we know the transform is that pretty much like the polar coordinate, right? So we know this is, and z is equal to z, right? So we just transform coordinate transform. All right, this is coordinate transformation. So that the gradient becomes to very similar to the Laplacian in the polar coordinate plus, okay, and this is equal to 0. So we have the same form in addition to the last one, because the z will be assigned to z in the cylindrical coordinate transformation. Okay, so that the idea, so the way to solve is pretty much like the way we solve the equation in polar coordinates. All right, so our next interesting thing, different thing is the spherical coordinate transformation. Okay, so for the spherical coordinate transformation, the x becomes 2r cosine theta and the sine phi. Okay, so we have r theta and the phi, and for y we have r sine theta and the sine phi. Okay, and for z we have r cosine Okay, so we have that. And then, in this case, the Laplacian comes to okay, so different from the symmetrical coordinate plus 1 over r square to 2 plus cotangent phi divided by r square the first order of partial derivative with respect to phi plus 1 over r square sin square phi partial derivative of u theta with respect to theta. Okay. So more complicated. Okay. All right, and we can express this expression in a more compact way. So if we take out r square, 1 over r square here, and combine them together, we will have r square. Okay, so this is 1 here. And also the other two terms about partial derivative with respect to phi. So we have 1 over sine phi, sine phi again, phi. Okay, so we combine these two terms together. And the last one, 1 over sine square phi square. Okay, so this is a more compact expressions for Laplacian, and this is equal to 0. Right? So suppose we want to solve the Laplace equation in the spherical coordinate system. Suppose that. And we further simplify our problem. So we assume circular symmetry for our problem means that all boundary conditions, initial conditions, are independent of theta. Okay, independent of theta. So this is circular symmetric, and so then the solution u r theta by t y must be independent of theta and e u cubed y is equal to u cubed r phi. And then u theta is equal to 0. Okay, so this term comes to 0. Okay, so this is just to simplify our problem. So suppose we have a boundary problem such that, and also initial value and initial conditions such that everything is independent of theta. Okay, so we have circular symmetry. That everything is independent of theta, and so the solution must be independent of theta too. And so that this partial derivative is equal to 0. Okay, so now, okay, the Laplace equation becomes to R square of 1 over sine phi. Okay, so this is third point, 11.1. And we assume with boundary conditions equal to R. Okay. So that's U R phi equal to F phi phi. So this is 12.11.2 and limit and another boundary condition. And the implicit is an explicit boundary condition at R, and an implicit boundary condition at either R equal to 0 or equal to infinity. Okay, for interior problem, this is for interior. I will explain that for exterior. And R equals 0, we will have is finite. And the limit equal to 0 Okay. Because we will consider the Laplace equations that out of ball. Okay, and so this is the true. Okay, this Laplace equation. Oh, I forgot to put 0. It is true for the space except r equal to 0, right? Except the origin. This is true. Okay, and we have a boundary condition at r equal to r. It's a sphere, right? So when r equal to capital R is a sphere. Okay, and we may consider interior problem means that we want to know, for example, the potential. Okay, inside the sphere, or we want to know the potential outside the sphere. So we were these two different kind of problem because they for interior problem, you know, we have well, it's I'm not a good drawer, so this is sphere. Okay. This is the origin. Okay. So this is a sphere. All right. And if we consider the interior problem, the region we consider is the three-dimensional region bounded by the sphere, so the inside sphere. The other problem is that we consider exterior problem. We consider the space except inside the sphere, right? So we have two possible problems to consider, right? For the boundary region, all right, the boundary is just a sphere, of course. And for the unbounded region, the boundary is also the what? The sphere. Okay, and also R into infinity, right? You can imagine you have a boundary in the infinity, right? You imagine that you have boundary in the infinity. So you have a boundary condition. You for any physical problem. You maybe represent the potential, okay, of and so that the potential will go to 0 at infinity. Okay, so this is a physically meaningful assumption. Okay, and for interior problem, at the center, you think that at the center you should have some potential too, and it's finite. Okay, so pair with the boundary. The boundary is the sphere. Okay, just the ball. All right, the surface of the ball is a sphere, right? But this is sphere. So we have an explicit boundary condition here, which we say is F phi. Okay. But for another implicit boundary condition, it depends on the problem. Okay, depending on the problem. One either is the interior problem, you are concerned with the U value, U tilde value inside the sphere, or you concern the U tilde value outside the sphere. So you have either interior problem or exterior problem. Okay, is that okay for you? Do you need me to explain more? Okay, so we'll go back to these two different kind of problem later. Okay, so now by the method of separating variable, relate. So relate U R phi equal to G R and H phi. Okay? So we will have 1 over G d dr r squared dg dr, which is equal to minus 1 over h times sine phi d d phi sine phi dh and d phi. Okay? So when we plug into here, we have this one, and this is, we said this is, and this is a function of r, this is a function of phi, and they are equal, so they must be equal to a constant. And we let this constant as lambda. Okay? This is a constant as lambda, so it's a constant. Okay, and from here we have two ODE. Now we have two ODE. So one is sine phi sine phi dh d phi plus lambda h equal to 0. So this is 12.11.4. Oh, 5. Sorry. And r squared d squared g dr squared plus 2r. Okay, I do the differentiation. So I have 2r in g dr minus lambda g equal to 0. 6. And this is a famous, this is actually the famous Euler-Cauchy equation. Okay? When lambda is equal to n times n plus 1. Okay? Alright? We learned how to solve the Euler-Cauchy equation when lambda is equal to n times n plus 1. And I will explain why the lambda should be equal to n times n plus 1. I will explain why. Okay? Because here, lambda can be any constant, right? Lambda can be any constant. Okay? So now, the thing is that, and how about the first one? Okay? By making W equal to cosine phi. This is not so familiar, so we make some transformation. Okay? So phi is in 0 to pi, so it implies that W will be in minus 1 to 1. Okay? So in this range. Okay, so when we do the change of variable, okay? Understand? So we have sin phi is equal to 1 minus x squared So we have that. We have, we see the d, this differential, right? This is the derivative with respect to y, can be changed as, okay? Right? And what is that? This is minus sine phi. And d, okay? So that implies that 1 over sine phi d phi is equal to minus d theta. This is the reason why we make such a change of variable. Because in here we will always encounter that this operator here. Oh, okay, so we can render to sine phi okay, you can think about that. Okay, so this one is minus dw, and the inside you have sine square phi, alright, and 1 over sine phi d phi here. And the ODE in 12.11.5 becomes, alright, so it becomes what? It becomes to dw 1 minus the square, because sine square phi is equal to 1 minus w square. Because minus becomes plus. Okay? Plus lambda h equals 0. And what is that? The Lambda equation. Remember that? This is the Lambda equation. So this is right with eigenvalue lambda. Okay. So now we have again we get a Sturm-Liouville problem again. Right, an eigenvalue problem here. Okay, and so a general solution so as discussed in section 11.5, a general solution okay, so of the Lambda equation is y equals to c1 y1 plus c2 y2. Okay, where with y1 is power series, okay, from 0 to infinity am, so it's a to k even part, and y2 is equal to k from 0 to infinity a to k plus 1, x to k plus 1, where a0 equal to a1 equal to 1, and we have a recursive formula am plus 2 is equal to m times m plus 1 minus lambda divided by m plus 1 times m plus 2 times am, for m greater than or equal to 0. So we have the power series solution here. Okay, we have power series solution. And as we know, if lambda, is not equal to n times n plus 1 for any, suppose lambda is not 10. If not, then the power series is infinite power series, okay? Because the coefficient cannot be 0, and right? Never. And we prove that. We put y1w and y2w are unbounded. Right? So they are unbounded at either up to the 1 or the end point. Okay? And it's impossible because we should have, I have to set h, I'm sorry, h. We solve h, it's not right. Okay, so, alright, so we let lambda equal to n times n plus 1. So if lambda 1 of y1 and y2 is an infinite series, which is also unbounded. It's either minus 1 or 1. Okay? Oh, I think I have to use 1. If not 1, oh no. Okay, yep. Anyway, H. So, alright, so one of the two independent solution should be infinite series, but which is unbounded at end point, so it's not suitable. Okay, so our solution, so with thus with lambda is equal to n plus 1, and we have a solution Hn, which is equal to Pn, and which is Pn cosine phi. Oh, and n can be, I'm sorry, 0, okay. Include n equal to 0. I'm sorry. Okay. So please change. Okay, so we have where Pn x is the larger function of order. Okay, so we solve the solution. Okay. So this is our solution here. And I have to stop here. Okay, and I will continue to complete the solution. But at this point, we know why lambda should be n times n plus 1. So that the second equation, the second ODE becomes to the Euler-Cauchy equation. Okay? Comes to Euler-Cauchy equation. Because lambda is equal to n times n plus 1. Okay? For all n. Okay. And it's very easy to solve the Euler-Cauchy equation. It's just a polynomial, a monomial, x to the nth power. It's very easy. Right. All right. So we almost solved the problem. Okay. And we will start a lecture at 1 p.m. on Thursday. Okay. So please remember, please come earlier at 1 p.m. Okay. On Thursday, and we will have quiz number 9. All right, from 2 o'clock. I'm sorry to exchange the schedule because I have a meeting in Taipei. I have to go to that in the afternoon. All right, so thank you and see you Thursday.